we've seen that it can be kind of handy to phrase derivative operators in terms of the linear operator capital D. So capital D was our name for the operator d dx. And this is a linear operator. Linear just means that if you have two functions, f and g, and you multiply them by constants and add them up, right? So if you take this linear combination of functions, then the operator distributes and the constants move outside the operator. So that would, for the operator d, this would produce this, a times derivative of f plus b times the derivative of g. So this is certainly a familiar fact for this particular operator, the differential operator d dx. So this is a linear operator. There are other operators that are linear, other transformations you can apply to functions that produce other functions and that are linear. For example, the integral is another linear operator. If you have a linear combination in here, the integral distributes and you can move constant multiples outside. So this is an integral linear operator. Now, in the early days of calculus, people experimented with other kinds of linear operators for other tasks. And one way of coming up with more linear operators that turned out to be pretty convenient is, right, if you start with a function of your independent variable, and we're going to start using t for our independent variable. One way you can come up with a way to transform this into a different function is to integrate this. You kind of have to pick what your bounds are going to be. Integrate this after multiplying it by some other function that you've chosen, and this function is a variable of s and t, and your integral is with respect to t. The result of this sort of thing is going to be a new function, but since the integral was with respect to t, t sort of gets used up as a variable, and so the resulting function is a variable only of s. In this context, this function k determines what the transform is, right? You can put in, once you've chosen your function k, you can put in any function f and you get capital F. So k together with the bounds determine what this transformation is doing, and k is called the kernel of the transformation. There's one particular choice for a kernel that turns out to be very convenient for working with differential equations, and it's this choice. So first of all, the bounds are going to be from 0 to infinity. And the kernel that turns out to be very nice for differential equations, at least one of them, is e to the minus st. So we're going to work with this transformation. The transformation that when you put in a function, it multiplies it by e to the st, integrates from 0 to infinity with respect to t, and that produces a new function of s. Another way to write the output, the result of this transformation, is with a script L and then little f in brackets like this. This transformation is called the Laplace transform. And it does turn out to be pretty convenient for differential equations for reasons that we'll see. You might think that this is a pretty bad choice for a kernel here because this integral is going to be pretty difficult to calculate for all but the simplest functions f. But it turns out that there are just enough cases where we can actually compute this integral that we can kind of build up a calculus of Laplace transforms so that we can figure out Laplace transforms without explicitly calculating this integral every time.